Okay, so let's talk a little about how computers encrypt info. There's two basic types of computer encryption. The one we're going to look at is called symmetric. There's one key, and it's based on using logic operations like exclusive OR and transitions. Asymmetric uses two keys, a public key and a private key, and it encrypts by using mathematical formulae. We're not going to talk too much at all about asymmetric. So symmetric works on the bit level. Consider an ASCII chart. You've seen an ASCII chart, and I have posted an example of an ASCII chart on Blackboard. So what would the bit pattern be using ASCII for the word Trent? Uppercase T, lowercase R-E-N-T. So if you check the ASCII table, you'll see that the code for capital T is 54 in hex, R is 72, E is 65, N is 6E, and T is 74. So we can use our binary hex table to convert these hex values into binary values. And this is showing the coding, so the code for Trent in hexadecimal will be 547265, 6E74, or in binary that long, ugly looking binary number. So how can we encode this? If we're using symmetric, we can do two basic things. We can do what's called rotate bits, or we can apply a logic operator, call it exclusive OR. So we'll take a look at both these. So rotating bits. We can rotate bits either to the left or to the right. So let's say we have this following set of bits. So let's say we want to rotate the bits 3 positions to the left. So the 3 bits on the very far left, 0, 1, 0, are going to rotate all the way around to the far right. So after we're done, from the far right, the 3 digits would be 0, 1, 0. As it shows here. So everything else has stayed the same, just the 0, 1, 0 has gone from the far left to the far right. We can also rotate right. So let's say we want to rotate 5 spots to the right. So in this case, our 1, 1, 0, 1, 0 would go from the far right over to the far left. And as you can see, that's what happened. So this is rotating bits. This is pretty easy. We can rotate left, rotate right, any number of bits we like. The nice thing about rotating is if we reverse the rotation, we get the original value back. For instance, if we took our number after rotating it 5 to the right, and rotated it 5 to the left, and then rotate it 3 spots to the right, we'd have our original value back again. What's an exclusive OR? This is a little trickier. Exclusive OR is a logic operator. What it does is it gives us back a 1 if and only if exactly one of the two values operated on is a 1. Otherwise, it gives us a 0. So 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0. And we do this column by column. So let's look at the example we have. We XOR it with this key. So this key is 1, 1, 1, 1, 4 ones, which is F, and 4 zeros, which is 0. If you XOR something with a 1, it's going to flip its value. It's going to change its value from a 1 to a 0 or 0 to a 1. If you XOR something with a 0, we get the original value back. So as you can see from the result, in the first column, say on the far left, 1 XOR 1 gives us a 0, 1 XOR 1 gives us a 0, 0 XOR 1 gives us a 1, and so on. The nice thing about XORs, if you XOR the result with the same key, we get back to the original value, which allows to decrypt our message. So let's say we want to encrypt the word Trent. So one way would be to find the bit patterns that represent Trent in ASCII. So just look on your ASCII chart and find the pattern for the capital T and small case r and so on. Then we're going to rotate it 3 positions to the left. Apply an XOR using the same slide as on the previous slide, so that's F0, and then rotate it 5 positions to the right. So this is our bit pattern for Trent. If you rotate it 3 spots to the left, the 0, 1, 0 that was on the far left is now on the far right. If we then XOR it with our F0, again we're going to change all the bits, so we're XORing with a 1 and leave all the bits the same. We XOR it with a 0. So again, if you look at the far left, 1 XOR 1 gives us a 0, 0 XOR 1 gives us a 1. And then we rotate it 5 spots to the right. So the 1, 0, 0, 1, 0 that was on the far right is now over on the far left. So this would be an effective encryption algorithm for encrypting Trent. In the real world, these algorithms have 17 or 19 different steps in order to encrypt the message. So our hex value for our encrypted value for Trent would be 929B, 1E, DC, 1A, and of course we get that from using our chart to convert between binary and hexadecimal. So symmetric cryptography is based on transformations and rotating, XORing, and asymmetric is based on mathematical functions. As such, it takes a lot more computing power to use asymmetric encryption, so it's typically only used on small files. You wouldn't use asymmetric encryption on a whole drive. If you wanted to encrypt, say, a whole hard drive, you would definitely use symmetric cryptography. One problem with using keys is how do we deliver, or using encryption, is how do we deliver the keys? So this is a challenge. Sometimes it's done out of band, meaning you just hand somebody the key values. If somebody gains the keys to your encryption algorithm, then they can decrypt all of your information. So it is important to keep the keys safe.